Here's a proof I did in class. We'll take that interval from a to b and divide it into subintervals from x naught to x sub n. Now this vertical axis in this graph will be the graph of the antiderivative. The beginning of this proof will begin with the right side, capital F of b minus capital F of a. This expression is essentially this distance from f of b to f of a, right there. And we can write that distance as a sum of all the individual distances. This one, which is the vertical distance from here to about there. And then for the next distance, we'll start at that same point and go down to the next boundary, maybe like that. So from x sub n minus 1 to x sub n minus 2, onward all the way down, I should say, till we get to the end, where we'll do the last couple ones. The second last one and the last one. All right, we have the right side of our theorem rewritten this way. The next step is to rewrite this long expression using summation notation. Before we do, just notice how these terms cancel each other out, and every pair will do that all the way down to the end. Leaving us only with f of x of n, which is f of b, minus f of x sub 0, which is f of a. All right, if we have the sum as I goes from 1 to n, look at the subscripts. If I starts at 1, we're actually starting on the right side. This is our 1, our first difference, our 2, our second difference, all the way to our nth difference. Therefore, our expression here looks like that, and you can check it. When I is 1, we get this difference. When I is 2, this gives us this difference all the way down the line. We can think of each of these domains as subintervals. The ith subinterval, the first subinterval, if I was 2, that would be from x sub 2 to x sub 1 would be the second subinterval. We can think of all those as subintervals. Now, the mean value theorem says that on each of these closed subintervals, there exists a c-value such that, well, let's remind ourselves very conceptually what the mean value theorem guarantees. It guarantees that on this closed interval between a and b, there exists a c where the instantaneous slope of your curve is exactly equal to the slope of the secant from a to b. So, for each subinterval, there exists a c such that the instantaneous slope of capital F's graph at c sub I is equal to the slope of the secant segment from x of I to x of I minus 1. Well, capital F is the antiderivative, so the antiderivative's derivative is little f. And let's rewrite the difference from x of I to x of I minus 1 as delta x of I. And multiply both sides by the delta. And here we are. For each subinterval, we have this relationship. So where do we go from there? We repeatedly apply the mean value theorem to every single subinterval. That will give us a new right side where for each term that gets added, this inside is the left side because we proved that these are equal to each other. All right, let's go ahead and do the substitution. Then all that's left is to take the limit as n approaches infinity. As the number of rectangles or subintervals diverges toward infinity, in other words, the limit as n approaches infinity, there are no n's in this expression, so the left side remains. while the right side is our textbook definition of the definite integral. Quod erat demonstratum.